This is lecture 36, and so let me just recap what we did last time. I will first put it down in writing. We reviewed a discussion of density evolution with respect to the belief propagation based decoding of LDPC codes. And then after that I actually stated what I called or what is called a concentration and convergence theorem. So, what this theorem is all about is it basically says that look, you did your density evolution under a tree like assumption, but what if it is not tree like? And this theorem says, well, it attempts to reassure you by saying, well, all is not lost, because with high probability you are going to perform just as good as you did in the tree like case. So, let me do the following, since I want to more or less complete a proof that I started out in this theorem, and I am going to take advantage of our technology, because our technology allows me to go back to the writing of the previous lecture, and I am going to use that to complete the proof. So, let us take a look at the statement of the theorem again. So, the theorem says that look, the difference between the number of messages passed during the Lth iteration along along all the edges going from a variable to a check node in the Lth iteration, the probability that it deviates significantly from the mean is small. Now, this probability is computed over all channel realizations and over all selections of dv/dc regular graphs, and I explained that last time. The second part actually says the difference between the average over this ensemble of channel realization and dv/dc regular graph, the deviation of this from the expected value of the number of incorrect messages in the tree like case is small, provided you make n the block length large enough. And if you put the two together, you will find that the probability, it tells us that the probability that if you pick a graph at random, that the number of incorrect messages that are passed during the Lth iteration along the edges from the variable to the check node, the probability that that deviates significantly from the average or from the number, the expected number that would be passed in the tree like case is small. Okay. So, that means that you so this P actually comes from belief propagation. So, that in a sense tells us that all our work on belief propagation was not in vain, because it has meaning when applied to a graph that is picked at random, which may not necessarily have a tree like neighborhood. Now, I also said that what we are going to do is we are going to prove this part, and then I am not going to prove this because it happens to be somewhat lengthy, but we will put these two together to actually conclude this. So, we were in the process of proving part B, okay. And so I said that look, let Zi, Z sub I be the number of incorrect messages passed along the ith edge Ei during the Lth iteration, okay. And Okay. Here then since there are n dv edges that go from variable to check node, the total number of incorrect messages is of course the sum of the number of messages along each of the n dv edges, and this is a 0 1 function because either an edge is carrying an incorrect message or it is not. Okay, and then we take expectations on both sides, and the expected value of this is nothing but the probability that this particular the message on this is actually incorrect. So, how do we compute that? Well, we are going to compute this probability by breaking it down using conditioning. So, there is a probability conditioned upon the fact that its neighborhood is tree like and that which is not. Now, I just want to make the other point here that this thing here, that this quantity here is by the way, this conditioning is, since we are talking about z sub I, so there is something that I need to perhaps mention here, which is that look, because of symmetry, this is the same no matter which particular edge you consider. So, this is actually equal to n dv times the expected value of z1, any particular edge, let us say that it is z1, and I will just make a note that this is by symmetry. By symmetry of what? By symmetry of the Tanner graph. I mean, if you take a look at the Tanner graph, all your density evolution really depends only upon the degree of the nodes, and since all of the nodes have same degree, you would expect that the number of incorrect messages is the same, okay, and that is the reason why you would have that this number is independent of the particular thing here. So, now in this let us actually compute, given that they are the same for all I, it is perhaps clearer if I say that what I am now doing is focusing on one particular edge, which is z1, okay. And now we are interested in knowing what is the probability that the neighborhood of that particular edge E1, okay, is tree like. And this thing here, probability that a particular message is incorrect, given that the neighborhood to depth 2L is tree like, this comes from density evolution. This entire quantity here is nothing but our P, okay. So, now with all of this information and also the other quantity here, I mentioned towards the end of the last lecture that when n is large, it turns out that the probability that if you fix L and let n go off to infinity, the probability that the neighborhood to depth 2L is tree like is greater than or equal to 1 minus gamma by n. Now, we can actually use this to say that therefore, the expected value of z1 on the one hand is less than or equal to p plus gamma by n, on the other hand it is greater than or equal to p into 1 minus gamma by n, which in turn is greater than or equal to p minus gamma by n. Okay, so how did I get this? Now, so I am interested in actually obtaining both an upper and lower bound on this quantity. And now I know, for instance, so let me put down what I know about the various quantities. I know that this quantity lies between 1 minus gamma by n and 1. Okay. I am interested in obtaining lower and upper bounds to this quantity. So, if I want an upper bound, I will replace this by 1. If I want a lower bound, I will replace it by 1 minus gamma by n. I know that this quantity is p. if I want an upper bound, this is replaced by 1, that is p, and now we know that the probability with which the neighborhood is not tree-like is less than or equal to gamma by n. And since z1 is a 0 1 function, I can always say that this is less than or equal to 1. So when I put all of this together, if I want an upper bound, I simply say this is p, this is at most 1, this is at most gamma by n, and that's how I get my upper bound here. That is, it's at most p plus gamma by n. On the other hand, if I want a lower bound, then what I do is, well, this whole thing is non-negative, so I ignore it, and then say just look at the first term and say that, well, it's greater than or equal to p into 1 minus gamma by n. Okay. So that's how I get this other term. And now I can write this as greater than or equal to p minus gamma by n. So from which it follows, therefore, that the expected value of z1 minus p in magnitude is less than or equal to gamma by n. All right. Now I know that if I want to relate this to the expected value of the total number of messages that are in error, I simply multiply it through by ndv. Therefore, the expected value of z minus n dvp is less than or equal to n dv gamma by n. And now what we do is we assume or choose n large enough so that gamma by n is less than epsilon by 2. Okay. And with that, therefore, the expected value of z minus n dvp in magnitude is less than or equal to n dv epsilon by 2. All right. So that was part B of the theorem, as you can see here. So we've actually proved part 2. Now part 1 uses martingale theory. What it basically does is that says, look, this is an expectation, difference between a random variable and its expectation, and what I can do is I can introduce a sequence of random variables, a chain of random variables, such that this is at one end of the chain, this is at the other end of the chain, and that chain actually forms a martingale, and use an inequality known as Azuma's inequality for martingales to actually derive this bound. It's somewhat technical and takes up some time. It's a very nice result, of course, but we won't actually spend the time to do that. We don't really have the time. So what I'll do now is I'll assume 1. Okay, so this was our result 1. So I'll assume that we know 1 is true and 2, and we'll just actually show that the two together imply part C. Okay, part C being this theorem here. Now if you look here, you'll see that we've shown convergence to the cycle free case. We've related the average in the general case to that in the cycle free case, and we are not going to go prove this. So let's assume that there is a concentration around the mean in the general case, and we'll put the two together to show that there is a concentration around the cycle free case. This proves 2, this proves 2. We will skip the somewhat lengthy proof of 1, and now to show 3, I will just make the following note. To prove 3 given 1 and 2, we argue as follows. The probability that z minus n dVp is greater than n dV epsilon is equal to the probability that z minus the expected value of z plus the expected value of z minus n dVp greater than n dV epsilon. Okay. So, now we have added and subtracted the expected value of z, and we have these two terms. But for large enough n, when the expected value of z minus n dVp in magnitude is less than n dV epsilon by 2. Okay. So, what we are saying in part B, we showed that when n is large enough, this difference is going to be small. So, the only way that this can be large is if this is large. Okay. So, in other words, is A, if A is the event that this actually takes place, then it must be that the event B where this is greater than a half of this must take place. Okay. So, we can actually say that this is less than or equal to probability that z minus the expected value of z is greater than n dV epsilon by 2, because the situation is something like this. You have an event A and you have an event B, and sorry, the other way around. You have an event B and you have an event A, and we were interested in the probability of event A, and what this actually says is that since A, this event given this implies the occurrence of this event, it means that the probability of A is upper bounded by the probability of B. Okay. And this and this, okay, so we have this, and but this we already have an upper bound for from the theorem. Z minus the expected value of Z is, if you go back to the theorem, that was the part A of the theorem. Okay, so from part of the A of the theorem, we know that its probability is small. So this is less than or equal to 2e to the minus beta epsilon squared by n from part A of the theorem. Okay. So, that proves the theorem. So, to summarize, what we have actually shown is that although belief propagation dealt with the case when you are working with neighborhoods that are tree like, all is not lost when you actually pick a graph at random from the ensemble of DV-DC regular codes, because you can show that with high probability, if you pick for large block length a graph at random, that the number of incorrect messages passed during belief propagation decoding is going to be very close to the number of incorrect messages passed in the tree like case. And in the tree like case, you can verify that you are going to get that number is going to be very small, provided your channel is not too bad. It is the usual thing that as long as the channel is not too bad, you can actually get reliable information transfer, and the same thing happens over here. Okay. With that, we have completed our discussion on the concentration and convergence theorem. So, now we will actually start a completely new topic, and which goes back to the title of our lecture 36, which is a construction for finite fields. Okay. All right. Now, just a few words about why we are interested in finite fields. Now, we are going towards in fact, we are going to go jump to a completely different class of codes, and these codes were the codes that were in vogue before the recent high level of interest in codes that are iteratively decodable, such as LDBC codes. The algebraic codes have a great deal of structure and in a sense are very good codes, except that they can be somewhat more difficult to decode, and they are not able to actually work with the soft information provided by the channel. Okay. But nevertheless, in many applications they can be of great interest, particularly the classes of BCH and Reed-Solomon codes are often the codes, default codes that you would use in particular situations. In fact, the most widely used code in the world today is the Reed-Solomon code, because it is found in all kinds of memories, in your CD-ROMs, in your high definition TV, all kinds of storage media use Reed-Solomon codes because they have excellent properties well matched for that medium. I have recently been involved in a couple of projects where the natural choice was a class of codes known as BCH codes, and again these are algebraic codes, very different in nature, at least in the way they evolved from these LDPC codes. So, they are based completely on algebra. So, we will make a complete switch from all the probabilistic arguments we have been making up to now, or in this recent discussion on LDPC codes, and make the jump now to the algebraic case. Now, typically, so these codes make use of the theory of finite fields. Up to now, finite fields are not new to us because we worked with the integers 0 and 1, which form a field. So, that is an example of a field that is finite. However, we want to work with a more general case of finite fields. Now, often what you will actually see is in textbooks, you will actually see that the entire textbook on coding theory begins by first teaching you finite fields. Now, I have deliberately refrained from doing that because the idea being that let us bring in finite fields only when you need it. So, up to this point in time we really did not need finite fields because binary codes will take you a long way, and binary arithmetic, but now we do need it for the class of codes that we are going to actually discuss. Okay, so, with that as background, let me get started. So, we now finite fields, there is two, I'll discuss this in two stages. In the first stage, what we will actually do is I will give you a construction for a large class of finite fields, and in fact it turns out that every finite field must have such a construction. So, in some sense this construction covers all finite fields, but in the beginning it is just a construction. So, which leaves you wondering, well, maybe there are other kinds of finite fields. Then we will actually switch gears, or we will shift, take a different perspective and say, let us forget about construction, let us try a deductive approach to finite fields. Let us say, okay, I have a finite field, what can I deduce about its internal structure, and we will actually join up with the construction by showing, well, if it is a finite field, it must have a structure similar, very much like the one that we had in our constructions, and therefore, so this brings the two viewpoints together, and now you know more or less all that you need to know about finite fields. Okay. So, I will just make a few comments then. So, first of all, finite fields are the basis finite fields are the basis upon which the widely used classes of BCH and read Solomon codes are built. All right. Then the other comment is that our discussion will begin. So, there is a constructive approach, and then there is a deductive approach. What we will actually do is we will start here and then we will go on to this, and that will bring us back here, okay, as I just explained to you. So, even within the constructive approach, what I would like to do, which I think will make for improved understanding, is to actually give you a toy example. Okay. So, let us begin with what you might consider a toy or a prototype example of a finite field. And I will motivate the discussion like this. Now, you know that with regard to real and complex numbers, you can think of the real numbers as you can actually think of the real numbers as of the complex numbers in this way. You can actually think of it as real numbers to which you adjoined an imaginary element I, which happened to satisfy the condition that I squared was minus 1. So, what this means is the collection of all polynomials in I, in this imaginary element I, having real coefficients. Okay. So, keep in mind that this I is R is imaginary, and we all, but having worked with it so much since your high school days, you now accept it as having a very concrete existence. You just think of it as the square root of minus 1 and you do not pay much attention to it. But the fact is that really there is no such thing as a square root of minus 1, right. So, how does one, so I want to actually give you an alternative viewpoint of the complex numbers, which will be useful in our discussion on finite fields. So, consider, think of the complex numbers as follows. We consider the ring of all polynomials over the real numbers modulo x squared plus 1. What does this mean? This means that all the elements, first of all, this is the ring of all polynomials in an indeterminate x over the real numbers, and this structure is not new to us. We have actually encountered this before. But what about this modulo x squared plus 1? So, in a way what you can do is you can pretend that what this is telling us to do. So, you should read this as r of x, you should modulo x squared plus 1, meaning that in all your calculations, either addition or multiplication, you can actually discard multiples of x squared plus 1. So, this is analogous, this is very much analogous to when you are working with the real numbers, and then you go mod, you go z, but you go mod n. Okay. You take the integers, but then you discard multiples of n. Now, there is one feature of this polynomial x squared plus 1, namely that it is irreducible, it cannot be factored over the real numbers. Now, if you take this the analogy here, for example, if n is 6, that 6 can be factored. So, if you want a more exact analogy, what you have to do is you have to replace this n with a prime. So, you look at z mod p for p a prime. So, the integers modulo p. So, just like we know that this forms a field, okay, we know that this structure forms a field, and we actually call this ZP. Now, I am being a little bit informal here, I am not writing out very carefully, because the idea is just to motivate you and you already have some idea. So, my point is that the complex numbers can also be considered to be this particular structure. Why is that? Because think about it, that is in R x mod x squared plus 1. What is x squared? Well, x squared can be expressed as x squared, right, plus 1 minus 1, adding and subtracting 1. But when you go modulo x squared plus 1, then you disregard this. So, these are treated as being equal to 0. So, this is minus 1. So, now this ring therefore contains an element such that its square is equal to minus 1. Okay. Now, so from a certain point of view, if you want it to be a little bit more rigorous, you really should think of the complex numbers like this. That is, it is the set of all polynomials in an indeterminate x where the coefficients are real, except that you are doing arithmetic modulo a polynomial x squared plus 1. But that is laborious, and I am sure that you much prefer the way we actually do it. So, how do we actually handle it? We say, well, but that is completely equivalent to actually saying that rather than r of x modulo this, we work with r I where I squared plus 1 is 0. In other words, we introduce a fictitious element, okay, which we call I, having the property that I squared plus 1 equal to 0. So, that now you are working with polynomials with I as coefficients. So, what do these polynomials look like? Now, because I squared is equal to minus 1, you never have to consider polynomials whose degree is greater than 1, because the moment you come into degree 2, you can fold it back, because you can say, well, the moment I run into anything which is degree 2, I can actually use it to come back to degree 0 or 0 in I. So, therefore, this is nothing but the collection of all elements of the form A plus IB, where both A and B are actually real numbers. Now, it turns out that finite fields actually can be constructed in a very similar way. So, the complex numbers, again to recap, so the complex numbers you can think of as being constructed as follows. You start with the real numbers, okay. Then you take an irreducible polynomial, which is x squared plus 1, and then you go r of x mod x squared plus 1, and that gives you another field. So, it turns out that if you start with a field, you go modulo an irreducible polynomial. Well, what does irreducible mean? It means that it cannot be factored. So, it is the analog of a prime number which cannot be factored. I will actually write these down a little bit more carefully, but just to give you the idea. So, that is your first step, that you go I of x mod x squared plus 1. Then you say that is laborious. So, I am going to replace x squared plus 1 by an x by an imaginary element I, and I am just going to assume that I squared is equal to minus 1, which is equivalent to saying that I is the square root of minus 1. And now I am going to work with polynomials in I over R. So, that is now how you actually bring in imaginary numbers. So, with the finite fields we do the same thing. Our starting point is not the real numbers, our starting point are the integers modulo p, zp. The integers modulo p, we know that they form a field, right, because the way we saw that was, we saw very early on that if you look at the integers mod n, then that is a ring, and that when n is a prime, then you actually have a field. So, this goes back to our early discussion on rings. You can actually go through your notes and look that up perhaps. So, your starting point, which was the reals in the case of the complex numbers, is now Zp. Then you hunt for an irreducible polynomial over Zp, and it turns out that no matter what degree you name, you will always find an irreducible polynomial. This is in contrast to the complex numbers, because in the case of the complex numbers, you only have an irreducible polynomial of degree 2, you do not have any other polynomial, okay. Everything else can be factored. So, or at least in the sense that well, you do, but once you actually gone from the real numbers to the complex numbers, any other polynomial can actually be factored over the complex numbers, okay. So, in some sense the only irreducible is x squared plus 1. Now, with finite fields, you actually have the integers mod p, and you take an irreducible polynomial. They exist for all degrees, and you go modulo that irreducible polynomial, and it turns out that that gives you all the known finite fields, all the finite fields that there are. Okay. So, with that, let me just start our more formal development, and I will start writing more carefully. So, we will now proceed to provide a construction of for finite fields of size q equal to p to the m for every prime p and every integer m greater than or equal to 1. When m is 1, we know that Zp, where Zp is the set of integers modulo p, we know that this is a field, is a finite field of size p. Okay. So we already know that how to construct a finite field for the case when m is 1. So, let us focus therefore on the case m is greater than or equal to 2. We focus therefore on the case when m is greater than or equal to 2. So, our starting point is this. Let f of x be a monic irreducible polynomial of degree m over f p. So, what does monic mean? Monic simply means that the highest degree coefficient is equal to 1. So, for example, supposing you had f of x equal to sigma f I x to the I is equal to 0 to m, then we say that f of x is of degree is monic of degree m if f sub m is equal to 1. Okay. So, that is what we mean by the highest degree coefficient. We actually look at all these terms. The highest degree term corresponds to I equal to m. So, we say that it is monic of degree m if f sub m is equal to 1. Now, the other word here is irreducible. So, what does irreducible mean? A polynomial and now just a clarification here. I have written monic in brackets here, and the reason for that is that whenever we speak of irreducible polynomials, we will automatically assume that the polynomial is actually monic. Okay, so, we will make that assumption. A polynomial, so perhaps for that reason a monic polynomial, again in brackets, f of x of degree, let us give this a degree, of degree d is said to be irreducible if it cannot be factored into the form f of x is equal to g of x h of x, where the degrees of both g of x and h of x So, we say that it is irreducible if it cannot be factored into this form. That is, if it is possible to express it as the product of two polynomials, both of which whose degree is first of all greater than 0 and strictly less than the degree of f, then it is not irreducible, otherwise it is. So, what are some examples? So, example, and by the way, our interest is in polynomials over, so whenever you speak of a polynomial, the polynomial is going to have coefficients in a certain field. So, our interest is actually in polynomials over the field f p. So, perhaps I should have added that here. So, let me just add that here. Over f p of degree d, all right. So, for example, supposing you take p is equal to 2, it turns out that here is a list of irreducible polynomials of various degrees. So, here is the degree and the list of irreducible polynomials of that degree. So, let us call this degree d, irreducible polynomials of degree equal to d. When the degree is 1, then you have x and you have x plus 1. When the degree is 2, you have x squared plus x plus 1. When the degree is 3, you have x cubed plus x plus 1 and x cubed plus x squared plus 1. When the degree is 4, you have x 4 plus x plus 1, x 4 plus x cubed plus 1, and then x 4 plus x cubed plus x squared plus x plus 1. So, this is it's also, this list is also an exhaustive list of all polynomials over F2 whose degree is as specified. Okay. So, these are the only irreducible polynomials of these various degrees. Now, remember, since we are setting p equal to 2, the coefficient field is F2, which is 0 or 1, and that is why all these polynomials have coefficients which are either 0 or 2, 0 or 1. You might, as an exercise, want to actually verify that these are irreducible. That is, if you take a polynomial like this, it cannot be factored into the product of two polynomials whose degree is less than 3 and greater than 0. And that is not hard, because you could just work your way up through this list. It is easy to show that these are irreducible. Then you consider all polynomials of degree 2, there are actually 4 of them, and you can show that this is the only one that is irreducible, because the others can be factored in terms of these. And so you work your way up through this list. So, that might be an interesting exercise. Just a comment here, it can be shown that for every prime p and every integer m greater than or equal to 1, irreducible polynomials of degree equal to m exist. Next, consider excuse me, consider the set f p x mod f of x, where f of x is irreducible of degree equal to m greater than or equal to 2. So, now what do I mean by this? So, and we have actually seen this before. So, this is the collection of equivalence classes where we define G1 equivalent to G2 if and only if f of x divides G1 of x minus G2 of x. Now, I will leave it as an exercise for you to verify that the reflexive symmetry and transitive properties hold. I see that we are almost out of time. So, just as a quick recap, I completed our discussion on the concentration and convergence theorems of LDPC codes. Then we shifted gears, switched to a completely new topic, started talking about algebraic codes, and I started introducing finite fields, and I am about to give you an example construction for finite fields, which happens to really be exhaustive in the sense that you can construct every possible finite field using this construction. Okay. So, thank you, and we will see you next class.